Looking deeply inside nature through the magnifying glass of science, designers extract principles, processes, and materials that are forming the very basis of design methodology. From synthetic constructs that resemble biological materials to computational methods that emulate neural processes, nature is driving design. Design is also driving nature. In realms of genetics, regenerative medicine, and synthetic biology, designers are growing novel technologies not foreseen or anticipated by nature. Bionics explores the interplay between biology and design. As you can see, my legs are bionic. Today, I will tell human stories of bionic integration, how electromechanics attached to the body and implanted inside the body are beginning to bridge the gap between disability and ability, between human limitation and human potential. Bionics has defined my physicality. In 1982, both of my legs were amputated due to tissue damage from frostbite incurred during a mountain climbing accident. At that time, I didn't view my body as broken. I reasoned that a human being can never be broken. Technology is broken. Technology is inadequate. This simple but powerful idea was a call to arms to advance technology for the elimination of my own disability and ultimately to the disability of others. I began by developing specialized limbs that allowed me to return to the vertical world of rock and ice climbing. I quickly realized that the artificial part of my body is malleable, able to take on any form, any function, a blank slate for which to create perhaps structures that could extend beyond biological capability. I made my height adjustable. I could be as short as 5 feet or as tall as I'd like. So when I was feeling badly about myself, insecure, I would jack my height up. But when I was feeling confident and suave, I would knock my height down a notch just to give the competition a chance. Narrow wedge feet allow me to climb steep rock fissures where the human foot cannot penetrate, and spiked feet enable me to climb vertical ice walls without ever experiencing muscle leg fatigue. Through technological innovation, I returned to my sport stronger and better. Technology had eliminated my disability and allowed me a new climbing prowess. As a young man, I imagined a future world where technology so advanced could rid the world of disability, a world in which neural implants would allow the visually impaired to see, a world in which the paralyzed could walk via body exoskeletons. Sadly, because of deficiencies in technology, disability is rampant in the world. This gentleman is missing 3 limbs. As a testimony to current technology, he is out of the wheelchair, but we need to do a better job in bionics to allow one day full rehabilitation for a person with this level of injury. At the MIT Media Lab, we've established the Center for Extreme Bionics. The mission of the center is to put forth fundamental science and technological capability that will allow the biomechatronic and regenerative repair of humans across a broad range of brain and body disabilities. Today, I'm going to tell you how my legs function, how they work, as a kind of case in point for this center. Now, I made sure to shave my legs last night because I knew I'd be showing them off. Bionics entails the engineering of extreme interfaces. There's 3 extreme interfaces in my bionic limbs: mechanical, how my limbs are attached to my biological body; dynamic, how they move like flesh and bone; and electrical, how they communicate with my nervous system. I'll begin with mechanical interface. In the area of design, we still do not understand how to attach devices to the body mechanically. It's extraordinary to me that in this day and age, one of the most mature, oldest technologies in the human timeline, the shoe, still gives us blisters. How can this be? We have no idea how to attach things to our bodies. This is the beautifully lyrical design work of Professor Neri Oxman at the MIT Media Lab, showing spatially varying exoskeletal impedances, shown here by color variation in this 3D printed model. Imagine a future where clothing is stiff and soft where you need it, when you need it, for optimal support and flexibility without ever causing discomfort. My bionic limbs are attached to my biological body via synthetic skins with stiffness variations that mirror my underlying tissue biomechanics. To achieve that mirroring, we first developed a mathematical model of my biological limb. To that end, we use imaging tools such as MRI to look inside my body to figure out the geometries and locations of various tissues. We also took robotic tools. Here's a 14 actuator circle that goes around the biological limb. The actuators come in, find the surface of the limb, measure its unloaded shape, and then they push on the tissues to measure tissue compliances at each anatomical point. We combine these imaging and robotic data to build a mathematical description of my biological limb, shown on the left. You see a bunch of points or nodes. At each node, there's a color that represents tissue compliance. We then do a mathematical transformation to the design of the synthetic skin, shown on the right. And we've discovered optimality is where the body is stiff, the synthetic skin should be soft. Where the body is soft, the synthetic skin is stiff, and this mirroring occurs across all tissue compliances. With this framework, we produce bionic limbs that are the most comfortable limbs I've ever worn. Clearly, in the future, our clothing, our shoes, our braces, our prostheses will no longer be designed and manufactured using artisan strategies, but rather data-driven quantitative frameworks. In that future, our shoes will no longer give us blisters. We're also embedding sensing and smart materials into the synthetic skins. This is a material developed by SRI International, California. Under electrostatic effect, it changes stiffness. So under zero voltage, the material is compliant. It's like floppy like paper. Then the button's pushed, a voltage is applied, and it becomes stiff as a board. We embed this material into the synthetic skin that attaches my bionic limb to my biological body. When I walk here, it's no voltage. My interface is soft and compliant. The button's pushed, voltage is applied, and it stiffens, offering me a greater maneuverability of the bionic limb. We're also building exoskeletons. This exoskeleton becomes stiff and soft in just the right areas of the running cycle to protect the biological joints from high impacts and degradation. In the future, we'll all be wearing exoskeletons in such common activities such as running. Next, dynamic interface. How do my bionic limbs move like flesh and bone? At my MIT lab, we've studied how humans with normal physiologies stand, walk, and run. What are the muscles doing, and how are they controlled by the spinal cord? This basic science motivates what we build. We're building bionic ankles, knees, and hips. We're building body parts from the ground up. The bionic limbs that I'm wearing are called biomes. They've been fitted to nearly 1,000 patients, 400 of which have been US wounded soldiers. How does it work? At heel strike under computer control, the system controls stiffness to attenuate the shock of the limb hitting the ground. Then at mid-stance, the bionic limb outputs high torques and powers to lift the person into the walking stride, comparable to how muscles work in the calf region. This bionic propulsion is very important clinically to patients. So on the left, you see the bionic device worn by a lady. On the right, a passive device worn by the same lady that fails to emulate normal muscle function, enabling her to do something everyone should be able to do, go up and down their steps at home. Bionics also allows for extraordinary athletic feats. Here's a gentleman running up a rocky pathway. This is Steve Martin, not the comedian, who lost his legs in a bomb blast in Afghanistan. We're also building exoskeletal structures using these same principles that wrap around the biological limb. This gentleman does not have any leg condition, any disability. He has a normal physiology. So these exoskeletons are applying muscle-like torques and powers so that his own muscles need not apply those torques and powers. This is the first exoskeleton in history that actually augments human walking. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal, healthy person wears the device for 40 minutes and then takes it off, their own biological legs feel ridiculously heavy and awkward. We're beginning the age in which machines attached to our bodies will make us stronger and faster and more efficient. Moving on to electrical interface, how do my bionic limbs communicate with my nervous system? Across my residual limb are electrodes that measure the electrical pulse of my muscles. That's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we model the missing biological limb, and we've discovered what reflexes occurred, how the reflexes of the spinal cord are controlling the muscles. And that capability is embedded in the chips of the bionic limb. What we've done then is we modulate the sensitivity of the reflex, the modeled spinal reflex, with the neural signal. So when I relax my muscles in my residual limb, I get very little torque and power. But the more I fire my muscles, the more torque I get, and I can even run. And that was the first demonstration of a running gait under neural command. Feels great. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transected nerves, through channels or microchannel arrays. On the other side of the channel, the nerve then attaches to cells, skin cells and muscle cells. In the channels of motor channels, we can sense how the person wishes to move. That can be sent out wirelessly to the bionic limb. And then sensors on the bionic limb can be converted to stimulations in adjacent channels, sensory channels. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone. This video shows Lisa Millette shortly after being fitted with 2 bionic limbs. Indeed, bionics is making a profound difference in people's lives.
Oh my God. Oh my God, I can't believe it. It's just like I've got a real leg. Now don't start running.
Now turn around and do the same thing walking up. Walk up, get on your heel to toe like you would normally just walk on level ground. Try to walk right up the hill.
Oh my God.
They're pushing you up?
Yes, I'm not even, I can't even describe it.
It's pushing you right up.
Next week, I'm visiting the centers. Thank you. Thank you. Thank you. Next week, I'm visiting the Center for Medicare and Medicaid Services, and I'm going to try to convince CMS to grant appropriate code language and pricing so this technology can be made available to the patients that need it. Thank you. It's not well appreciated, but over half of the world's population suffers from some form of cognitive, emotional, sensory, or motor condition. And because of poor technology, too often conditions result in disability and a poorer quality of life. Basic levels of physiological function should be a part of our human rights. Every person should have the right to live life without disability if they so choose. The right to live life without severe depression. The right to see a loved one in the case of seeing impaired. Or the right to walk or to dance in the case of limb paralysis or limb amputation. As a society, we can achieve these human rights if we accept the proposition that humans are not disabled. A person can never be broken. Our built environment, our technologies are broken and disabled. We, the people, need not accept our limitations, but can transcend disability through technological innovation. Indeed, through fundamental advances in bionics in this century, we will set the technological foundation for an enhanced human experience, and we will end disability. I'd like to finish up with one more story, a beautiful story. The story of Adrienne Haslett Davis. Adrienne lost her left leg in the Boston terrorist attack. I met Adrian when this photo was taken at Spaulding Rehabilitation Hospital. Adrian is a dancer, a ballroom dancer. Adrian breathes and lives dance. It is her expression. It is her art form. Naturally, when she lost her limb in the Boston terrorist attack, she wanted to return to the dance floor. After meeting her and driving home in my car, I thought, I'm an MIT professor. I have resources. Let's build her a bionic limb to enable her to go back to her life of dance. Brought in MIT scientists with expertise in prosthetics, robotics, machine learning, and biomechanics. And over a 200-day research period, we studied dance. We brought in dancers with biological limbs, and we studied how do they move, what forces do they apply on the dance floor. And we took those data and we put forth fundamental principles of dance, reflexive dance capability, and we embedded that intelligence into the bionic limb. Bionics is not only about making people stronger and faster. Our expression, our humanity can be embedded into electromechanics. It was 3.5 seconds between the bomb blasts and the Boston terrorist attack. In 3.5 seconds, the criminals and cowards took Adrian off the dance floor. In 200 days, we put her back. We will not be intimidated, brought down, diminished, conquered, or stopped by acts of violence. Ladies and gentlemen, please allow me to introduce Adrian Hoslett Davis, her first performance since the attack. She's dancing with Christian Leitner.
Ring my bell, ring my bells. 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 Sometimes you love it, sometimes you don't. Sometimes you need it, then you don't, and you let go. Sometimes we rush it, sometimes we fall. It doesn't matter, baby, we can take it real slow.
Ladies and gentlemen, members of the research team, Elliot Rouse and Nathan Verkartzi. Elliot and Nathan. Woo.